Adamantium, bolognium, dilithium. Element 0, Kryptonite. Mythril, Netherite, Orichalcum, Unobtanium. We love the idea of fictional elements with miraculous properties that science has yet to discover. But is it really possible that new elements exist beyond the periodic table? Science fiction in particular often imagines artificial, or yet-to-be-discovered elements whose incredible properties will propel us into our star-faring future. But for anyone who has studied a bit of chemistry, this seems far-fetched. The elements of the periodic table are defined by the number of protons in the atomic nucleus, the atomic number. So how can there be gaps for new elements? Sure, we could keep adding protons at the top end of the periodic table, but those seem to be hopelessly unstable, and so hardly useful for building warp drives. But the fact is, gaps in the periodic table did exist, atomic numbers that seem to appear naturally. And it may also be that the current upper end of the periodic table is just another such gap, beyond which may exist an island of stability containing useful elements never before encountered. To understand the possibility of new artificial elements, let's start with the story of the first artificial element. We begin all the way back when Mendeleev figured out the periodic table. He arranged the known elements according to their atomic weight, and noticed periodic recurrences of chemical properties as atomic weight increased. We now know that chemical properties depend on the number of outer shell or valence electrons, which increase by 1 every time you add a proton to the nucleus, until the shell fills and you start over, filling the next shell up. Although he didn't know about protons, Mendeleev did notice gaps in his periodic table. He correctly interpreted these as 4 elements that had yet to be discovered. He was even able to predict many of their properties. Over time 3 of these elements were discovered and the gaps were filled with scandium, gallium, and germanium. But there remained a missing element, right between molybdenum and ruthenium, which we figured out had to correspond to a nucleus with 43 protons. For 7 decades chemists searched for element 43, but it was nowhere to be found in nature. It was eventually discovered, but not in nature. In 1937 Italian physicist Emilio Segre got hold of some molybdenum foil that had been part of Ernest Lawrence's newly invented cyclotron particle accelerator. The foil has been rendered radioactive in the accelerator, and Segre and his colleague Carlo Perrier were able to show that some of the molybdenum had gained a proton, transmuting it into element 43. They named the new element technetium after the Greek word for art or craft, so in a sense its name means crafted element. It's a silvery gray metal with chemical properties somewhere between manganese and ruthenium, the elements above and below it on the periodic table, just as predicted by Mendeleev. So why did we have to produce technetium artificially, when all the other elements can be found in nature? Well, actually technetium is produced in nature. Just like other heavy elements, in the core of massive stars. Those elements eventually find their way into planets, which form from the guts of those stars after they explode as supernovae. But technetium is so unstable that by the time the Earth pulled itself together from the detritus of dead stars, all the technetium was long gone. You're probably familiar with the idea that elements can be unstable. A more common term is radioactive, which we tend to associate with very heavy elements like uranium and plutonium. For those, the instability sort of makes sense. Their nuclei are enormous, so you might expect they'd have trouble holding themselves together. But actually any element on the periodic table can be unstable. More accurately, every element on the periodic table has unstable isotopes. Isotope is the word for different versions of the same element with different numbers of neutrons. For example, a carbon atom has 6 protons in the nucleus. The isotope of carbon that also has 6 neutrons is called carbon, 12 for its 12 total nucleons, and it's perfectly stable. Now an atom with 6 protons and 8 neutrons is still carbon-14, but it's not stable. It has a tendency for one of its excess neutrons to transform into a proton after ejecting an electron and a neutrino, which transmutes it into nitrogen. The half-life of carbon-14 is around 5,700 years, although we do encounter it in nature because it's created when cosmic rays hit nitrogen nuclei in the atmosphere. We say carbon-14 is an unstable isotope of carbon. Every element has unstable isotopes. Some elements only have unstable isotopes, for example, any with more than 83 protons, but also weird exceptions like technetium. As well, element 61, promethium. And there are different shades of instability. For example, technetium, 97 has a half-life of 4.2 million years, while technetium, 96, has a half-life of 51 minutes. larger atomic number tends to yield fewer stable isotopes and shorter half-lives. Elements with more than 118 protons decay so quickly that we've never been able to detect one in the lab. Ultimately, stability depends on the balance between protons and neutrons in the nucleus. You might think that after a century and a half of thinking about nuclear physics, we'd have all of this figured out. But actually the dynamics of the atomic nucleus are so complicated that it takes sophisticated computer modeling to understand any but the lightest elements, and many mysteries still remain. But we're getting there, so let's see if we can at least lay out the competing influences at work. An atomic nucleus is a place of extreme forces in delicate balance. On the one hand we have the electromagnetic force trying to force apart all those positively charged protons. And the strength of that force is great due to the proximity of the protons. On the other hand, we have the even stronger strong nuclear force holding the nucleons together. We talked about how the strong force holds protons and neutrons together. The story of how it binds entire nuclei is even more complicated. It involves sending virtual quark packets, mesons, between the nucleons. The details deserve their own episode, but the important thing to know is that it's a short-range effect. If a nucleus gets too big, the strong force can't keep things together and various types of nuclear decay become inevitable. Although the strong force vanishes quickly, its strength doesn't change much over the short distance where it actually works. However, electromagnetism just keeps getting stronger the closer two electric charges get. That means electromagnetism can overwhelm the strong force if protons are too close together, which is another way to destabilize the nucleus. That's why neutrons are so useful. They help separate protons so that the strong nuclear force stays stronger than electromagnetism. For smaller nuclei up to an atomic number of 20, an even split of protons and neutrons is usually the most stable. But for heavier elements, more and more neutrons are needed to provide that buffer, reaching neutron-to-proton ratios of 1.5 or more. But this is only part of the picture. It doesn't explain why the difference of a single neutron can mean a huge difference in stability. It also doesn't explain why there's no stable isotope of technetium. To understand that, we have to move beyond the common representation of the nucleus as a muddled blob of protons and neutrons. We have to think of these nucleons as having energy levels, just like electrons do. You may remember the octet rule from your chemistry classes. If an electron shell has 8 electrons, it is stable. That's the reason the noble gases don't interact with anything, because their electron shells are already complete. Something similar happens in this case. There are magic numbers which complete nuclear shells. They are 2, 8, 20, 28, 50, 82, 126 for neutrons, and 2, 8, 20, 28, 50, 82, 114 for protons. The closer a nucleus is to those numbers, the more stable it will be. The magic numbers are all even, and that's because nucleons pair up according to their quantum spin, just like electrons in their shells. One spin up and one spin down results in a net zero spin. This sort of spin coupling means that even if we aren't at a magic number of protons or neutrons, nuclei still prefer to have even numbers of protons, or even numbers of protons plus neutrons. Pairs of up-down nucleons form these stable little spin-zero partnerships in so-called nuclear pairing interactions. Having a rogue proton or neutron with an uncancelled spin seems to be bad for stability. Let's see if we can understand the instability of technetium using some of this. Sure, we can see that 43 is not a magic number of protons, nor is it even like its more stable neighbors molybdenum and ruthenium. But the nearby odd-numbered elements like the 47-proton D silver have perfectly stable isotopes. Even giving technetium a magic number of 50 neutrons doesn't help. Nor does giving it a total even number of nucleons. Why, for example, does technetium 97 survive for 4 million years but Tc96 decays in under an hour? It seems there are more mysterious forces at work besides neutron padding, nuclear shell filling, and spin coupling. It turns out there are no simple set of principles to determine nuclear stability. There are so many factors at play that the only way to figure this out is to simulate the nucleus. And we've had some remarkable success doing this using computational techniques like density functional theory, which we explained in a previous episode. These models are still not perfect, but they make many predictions we've verified, and some predictions that we haven't. For example, the island of stability. When we combine our experimental data with our simulations, we can make graphs like this one. Here we can see the magic numbers. Elements with a magic number of protons have more stable isotopes, and there tend to be more isotopes with a number of neutrons close to the neutron magic numbers. Patterns emerge, but not so as to give us Clean rules for what is needed to yield a stable nucleus. As for the unstable ones like technetium, well, they have unlucky spots in terms of not having magic or even numbers of protons, and for whatever complex reasons there is no configuration of neutrons that can stabilize that unhappy nucleus. So, are there elements not on the periodic table that humans can or have invented? Well, there are many. Nature can make these, but unless that production process is ongoing on the Earth, like with carbon-14, short-lived unstable elements are extremely rare in nature, only appearing briefly in the decay chain of other longer-lived unstable elements. The first was technetium, but we've now synthesized 24 artificial elements, filling in Mendeleev's gaps, and also extending the periodic table all the way 118 Oganesson, with its half-life of 0.69 milliseconds. There are elements beyond that, but we haven't made one last long enough to unambiguously detect them. But this isn't the end. I've hinted at this island of stability. Our calculations show that there may be more magic numbers for large numbers of protons and neutrons beyond the current periodic table. And our computer simulations agree. We aren't sure what these magic numbers are, but apparently they are in the neighborhood of 184 for neutrons, and 126 for protons. And they could have half-lives of millions of years. These stable-ish elements would appear here on the graph from before. A small island of stability in an ocean of hopelessly unstable isotopes, but we have not been able to reach it with the same techniques we use to craft the other artificial elements. If we want to get there, our conventional nuclear reactors and particle accelerators will not be enough. We will have to come up with something new, but why should we even try to get to the island of stability? I mean, it's nice to get to name an element. But other than that, would such a discovery have any impact on the world? Well, probably, and possibly a large one. The eras of humanity are named by the materials we have mastered at the time: the Stone Age, the Bronze Age, the Iron Age, into the current Silicon Age. And new artificial elements have proved invaluable. For instance, technetium is used all the time in medical imaging as a contrast agent, and in this case its short half-life is actually an asset. By using an isotope with a half-life of only 6 hours, we can greatly reduce the amount of radiation the patient will be exposed to, while also being able to get useful images. Plutonium is another example. No stable isotopes, but we can breed it from uranium in nuclear reactors, where it becomes a critical part of the fission process in certain reactor types. Millions of people rely on it for their electricity. And then there's americium, created by bombarding the plutonium in a cyclotron to kick it one up on the periodic table before a complex chemical extraction process. Americium is critical for smoke detectors. So it's an artificial element that has saved many lives. The elements we will discover in the island of stability will be very heavy, initially hard to synthesize, and somewhat radioactive. But some will surely have unexpected and perhaps powerful applications. We discover hints of these islands of possibility just beyond the bounds of the known. What can we do but hold our breath and leap towards them, hoping to gain new ground in humanity's journey to further and future horizons of spacetime? As always, a huge thanks to everyone who supports us on Patreon. We seriously would not be here without you. Today's special shout-out goes to Glenn Sugden, who's supporting us at the Quasar level. Glenn, as thanks for your generous support, we're naming element 267 after you. Sugdenium is great. It's mildly radioactive, extremely useful in medical imaging, and is the critical catalyst for low-temperature fusion. On top of that glows a lovely shade of violet. Glenn, thanks for your support. We'll ship you a gram of sugdenium as soon as it's invented. In our last episode we talked about grabby aliens. That's the hypothesis that says that the future emergence of new civilizations has to be cut off at some point, or else humanity is too surprisingly early to the universe. And the cutoff is when the universe is fully colonized by, grabby aliens. Elia Zayin has a thoughtful criticism of the use of the Copernican principle to argue that we can't especially early in the universe. To paraphrase, even if there's a very low chance of any given civilization being one of the first, someone has to be first. So there's always going to be one civilization that ends up confused about why it's so early. So here you get to the most contentious aspect of anthropic reasoning. If I argue that I should find myself in the most typical circumstances consistent with my existence, what circumstances does that preclude? Nick Bostrom's self-sampling assumption tries to clear this up. It says that all other things equal, an observer should reason as if they are randomly selected from the set of all actually existent, past, present and future observers in their reference class. So the trick is figuring out what your reference class is. For example, if I define my reference class as a biological being, then I don't have to be surprised that I don't find myself somewhere uninhabitable. But that permits the 4 billion years of habitability prior to my birth. Why am I in the least brutal of those 4 billion years? Just lucky? But if I define my reference class as those who are able to formulate anthropic arguments, then it's less surprising that I live in a modern civilization. But then why can't I define my reference class as those who observes an empty universe? After all, I am my mental experience, and the mental experience of seeing an empty universe is what got me asking these questions in the first place. Being a member of an early species is one of the few circumstances consistent with what I am. You could say that this is too restrictive a way to define your reference class, but the fact is there is no clearly correct way to do that. All of this anthropic stuff is quite muddy. Tristan Cleveland points out that life may have had the potential to arise many times on early, except for the fact that once one incident of life got started and made progress, it would be very difficult for it to happen a second time. That second incidence would surely be eaten by the now more evolved first incidence. Indeed, we see that the DNA of all life clearly came from a single common ancestor. So if this dynamic happened on Earth, it makes sense it could happen across the universe. And that's exactly what the study we discussed is suggesting. That the emergence of new civilizations is eventually precluded. They may not be eaten, but they can't emerge naturally in a fully colonized universe. Several of you were pleased by the idea that we might be thought of as the ancients by the civilizations that followed. For example, Medic likes that we might one day be referred to as the old ones, with our ancient tech and ruins scattered across the universe. Let's just make sure we're the all-wise, benevolent type of old ones, rather than the tentacly Lovecraftian type. Because you know that's another solution to the Fermi paradox, that the first civilization became cosmic horrors, obliterating anything that comes after. Just like life on Earth probably did. If all this is inevitable, then I guess we want to be early, better us than them. Or we just hide. Of course, it's exactly this thinking that gets you the dark forest solution to the Fermi paradox. Damn it.